Welcome back, and we are very happy to have Jarosław Kędra, and we will ask the question of free groups bi-invariantly quasi-isometric.
Thank you very much, Lee. And thanks for coming for the talk. I'm used to talking without chalk in my hand, so I don't know what I will do with my hands, but probably in the past. This is a joint work with Assaf Libman. So I would like to explain the notions which appear in the title. So we start with the group. We take, for simplicity, a finite generating set, and S bar, I make the set invariant under conjugation. So I take union of all the conjugates of the generators and their inverses. So now the set is symmetric. An element is generated or the inverse also in the set, and every conjugate is also a generator. Then look at the word of the group associated with that set. So this is the shortest word in the generators. So if you think about the finitely generated group, it's the shortest word in the generators and their conjugates. The metric associated with the norm is defined like this. So the norm is, by definition, invariant conjugation. So the norm of an element and the norm of conjugate are equal. And if you define a metric like that, then because of the conjugation invariance, you have this equality, and the metric is binary, meaning that the group acting on itself by multiplication from the left and from the right are isometries. In this talk, my group will be the free group generated by n elements, or well, sometimes n will be m. And so I'm restricting myself to this case. So let's look at a few examples. A non-abelian free group of rank 2, the norm of a generator to the power n is n. The norm of a commutator is 2, because you can see it as A times a conjugate of A inverse. Okay, so 2 generators. The norm of a commutator to an odd power is the exponent plus 1. The even power, there is a typo. So this should be 2n, not commutator square times n. So it's the exponent plus 2. If you take an element like this, the next line, then it can be expressed as a product of 4 conjugates and generators. And the curious fact is that if you take a square of this element, it's also a product of 4 conjugates. So as far as I know, this is the smallest element with that property, and we know a few more. So this list of examples is supposed to tell you that this metric is not very obvious. If you think about the K graph of this metric, it's horrible, because you have infinite in any generator, so it's locally infinite graph. And, well, I can say something about the graph, but maybe not in this talk. Another thing, if you take z squared, you can embed free abelian group into the free group by this formula, and this is an isometric embedding. So, for example, people who are used to the fact that the free group is hyperbolic, with this metric it is not, it contains flats, and in fact it contains flats that are arbitrarily high. This norm can be quite efficiently calculated. So one of our colleagues wrote a Pro computer program which calculates the norm. So then there is an algorithm for calculating the norm, and it's quite efficient. So some of this computation comes from that software. So Irakli in his talk had fun facts. So maybe let me try. Fun fact. This norm was first investigated and discovered by biologists. So if you think of an element in a free group, which is a product of conjugates, you can write the element in a string. And if you have a bit of cyclically reduce something, then something you conjugate by, then another thing, you can kind of glue the conjugating word and have the cyclically reduced balloon like that. So this is what actually happens in RNA chains. And biologists were discovering this kind of forming patterns of RNA chains, and they were interested in the size of those balloons. This is exactly that norm. So if you translate the amino acids into AB and A inverse, B inverse, this is exactly what happens. So this algorithm, we in fact rediscovered after the failure without knowing it. So that was a fun fact. So we have these two metric spaces. Take your favorite free group, non-abelian free group from N, another from N. You have these metric spaces, and the first stupid question you ask is, are they similar? Are they quasi-isometric? If you are maybe you study groups with metrics associated with finite relating set, they are. So the inclusion of a finite index subgroup, like here, so for example, F7 into F2, can be included as finite index subgroup, is a quasi-isometry. In fact, this works in more generality. Inclusion of a finite index subgroup is always quasi-isometric, and that is classical results of Libman and Schwartz.
There's a more question, which is what happens if you change the generating set for Fn?
As long as it is,
Like, so if there are different finite ones, but then you conjugate, you do the.
as long as you take conjugates of the finite set,
Yeah.
it's finite.
Oh, okay. So this is very.
There is, we retain a little bit of standard geometric group theory equations. But if you have two groups of different ranks, we don't know. In classically, the inclusion of finites in the subgroup is a quasi-isometry. Here, that's the question. Also, this is a question from my talks. What I meant by bi-invariant with quasi-isometric is, are the free groups quasi-isometric when equipped with those metrics I defined? So maybe what is a quasi-isometry? So let's contemplate the definition. So we have two metric spaces, and the map between them, it's a quasi-isometry if there are two numbers. So let's look first at the second equality and forget about D. If you forget about D, this second equality means being Lipschitz, so like classical notion from the course of metric spaces. Additive constant means, Lipschitz can stretch, and this additive constant can do some noise. The left-hand side means that when you are mapping the source to the target, then you don't squash it too much, then it retains shape. So, for example, if the left-hand side inequality holds, we call it quasi-isometric embedding, even if it might not be injective. Second condition, which we call quasi-subjectivity, is that every point in the target is very close to the image. So I chose the constant to minimize the number of letters used in the so the D's and C's are gone. Example. The inclusion of infinite cyclic subgroup in the real numbers is quasi-isometry. So it's okay. You can check this directly. And the inverse is taking the floor function, for example. So you see, this is also quasi-isometry, and it's not injective. Okay, so it's satisfied the left-hand side inequality, that is something objective. The most geometric example is the inclusion of the orbit of the fundamental group into the universal path. If N is somewhat manifold, this is also a quasi-isometry, where this manifold is equipped with the Riemannian metric full life monsters. So the word metric here with this finite generating set and the Riemannian metric of the universal cover, these are quasi-isometric. I said a little bit about that. If you take a three-dimensional Heisenberg group over the integers, and its Abelianization, then if you equip these guys with the bi-invariant metric associated with the finite generating set, this is only bi-invariant, so that Abelianization now is quasi-isometric. So, and it can be generalized. So, for example, finite generated real potent groups and bi-invariant are quasi-isometric in their Abelianizations. Yes.
It seems like always your examples, some kind of platformic motion is always a finite in the example where there's no head. Like, for example, Amy's contact manifold, R1Z, this one. G mod H is finite.
Well, that's hard because if you can find present the group, it's a fundamental group of compact manifold. Almost it.
Very good.
So, okay, maybe one more example which we would like to think. Replace this guy with Thomson's group F. The Abelianization is the same, and it's also quasi-isometric. The reason for that is that the commutator subgroup in these groups is bi-invariantly finite diameter in the ambient. So this, I don't think in this consideration that there's a lot of time used. It's kind of, it's weird. That's all I can say. Sometimes, okay, let me maybe introduce some tools which are not one. Okay, the answer to the question, we don't know. What we can do is this. The obvious candidate is low. So I told you before that the inclusion of a finite index subgroup between previous was classically bi-isometric or finite generating set. In our world, it's not. But the general statement is that if you take a homomorphism from one free group to another, it is quasi-isometry if and only it is an isomorphism. So this is what I would like to explain in the talk. Okay, that's a hammer. A hammer, the main hammer is for the quasi-morphism. So quasi-morphism is a function on a group such that if you calculate this, it's the boundary. So if you want to check whether it's a homomorphism, it's not necessarily a homomorphism, but within bounded error, it's almost. So that's why it's well. Such function exists. I'll tell you in a moment. It's called homogeneous. Well, when it is homogeneous as a function, and the main property of those functions is that if it is bounded on the generating set, or on a set whose conjugate generate, then it satisfies this property that the absolute value of the value of an element bounds below after a constant the norm of an element. So if I want to show that some element has a big norm, all I need to do is find a quasi-morphism which evaluates to something non-zero or big, so I can have a. And the main point is to have enough quasi-morphisms to play games. So here is the main example. Take a reduced word in the free group, your favorite word. A function phi sub w is defined like this. I give an element G. I pick your element W, and I count disjoint copies of W inside G. That's this edge. Then I take W inverse, and I count disjoint copies of W inverse in G, and I subtract. Okay, so let's do some testing. If my W, so okay, let's do this for a free group on two generators, and the two generators are A and B. So if W is A, we get a projection on Z. That is some projection from F to Z, which counts the number of generators A. So nothing interesting, a homomorphism. But if you take a more complicated word, well, you count this, and why is it not a homomorphism? Well, if you take G and H, then there might be some cancellation of the junction. And if you count the words here, if some cancellation happens, then this counting might be a little bit screwed. But if we are counting disjoint copies of W and G, then this number P, which is called the defect of a quasi-morphism, is at most 2. By hand, you can prove probably that this is at most 3, but with a little bit more trickery, you can reduce it to 2. So this is done in the fantastic book by Daniel Caligari called State of the FCL. Okay, so this is my main example of a quasi-morphism for this talk. This will be enough for what I want. Maybe I should say that on a free group, non-abelian free group, there are plenty of quasi-morphisms like that. You can imagine it's going to take the word W, whatever you like. So it's this set of quasi-morphisms is really huge. As a vector space, because they're really valued, it's uncountable dimension.
Do these things survive in some portion of homology like?
Okay, so if you have such a function, if you look at the defining equation, inequality, so the left-hand side is the absolute value of one of the one of the boundary. So as a two cycle, it's a coboundary, so nothing interesting. But people invented something with boundary. So it defines bounded two cycle. But because it's a boundary of something which might be unbounded, it survives in the bounded second homology. So the second is that the second bounded homology of the free group is huge, although the second homology of the free group is 0. Yeah. Okay, so there is a homology but bounded that has a key.
How big is this group side quasi-morphism inside of quasi-morphism?
Well, as big as the not, I don't think there are for different words they might be equivalent. I don't know.
I mean, how big is the quotient? All quasi-morphisms are very
I mean, if you say it was uncountable, then this is.
No, there are more quasi-morphisms than this one.
Yeah.
Okay, and this guy is called small counting quasi-morphism. So the big one is that we count not necessarily disjoint copies, but forget about it. Okay, we're counting disjoint copies. The reason is that the digit is small. So this is only this one will be enough for the proof of the theorem I stated before. Okay, here is the proof. Case 0, it's enough to consider injective homomorphism. If it has a kernel, then a huge subgroup is equal to 0, so it cannot be a quasi-isometric embedding. So unbounded set is squashed to something to one. So let's assume that it's an inclusion of a subgroup. Case one, suppose the subgroup is finite index. And this is what you do. I am on the left-hand side, on the domain of my model. I want to find two elements which are not conjugate in Fm, such that if I include them in Fn, they become conjugate. So you can find it. For example, take an element of Fm, say, which is not the proper power. It's a technical, but it's important in the proof. Go to Fm, conjugate it with something which is not an element in Fm. So you have two guys conjugate, and no, start with an element which is in the core sum. So it's normal. If you conjugate, it's also in the core subgroup. So you have two cyclic subgroups, which are conjugate in the green side and non-conjugate in the blue side. And now you play the game. Take G.
Yeah.
In the core subgroup of Fm. Fm is a finite index, so it contains a normal in Fm subgroup, also finite index.
Okay.
Take G there. Go to Fm. Okay. Conjugate with someone which is not in Fm. So you have two guys conjugate. Exercise, they are not conjugate here. Another exercise, if you have two non-conjugate elements, you can find a quasi-morphism which distinguishes them. So for example, take a small quantum quasi-morphism defined by one of the types. And then if these two values are distinct, if you multiply it by k, you have these inequalities, which means that the norm of this guy is k times a number. So this set of all elements g to the kh k inverse is unbounded in my source. If I go to the target, if I look at this element, well, hk is a conjugate of g. But now this is conjugate of u times u. So the triangle inequality means that the norm of this is twice the norm of u. So it's bounded on this. So what I constructed here is a subset in the source which is unbounded, and the image in the target became bounded. Okay, so this is not a quasi-isometric object. Okay, it's very distinct. Unbounded set became bounded. So if your subgroup is of finite index, it's heavily distorted. It's not a quasi-isometric object. So this is case one. Same way with the case, what happens if my subgroup is of infinite index? Some finitely generated subgroup of infinite index in the free group, you can find a quasi-morphism, which is non-trivial, which vanishes from this subgroup. So, corollary of this fact is this group is not quasi-subjective because the quasi-morphism, so we have this subgroup on which the quasi-morphism is zero and growing to infinity in some other elements, which means that you can find elements which are arbitrarily far away from yourself. Okay, so it's not quasi-subjective. So this is the, so Palliatini and Rolli has a very nice argument for that. But before we discover this result, we proved it ourselves. And I will show you the proof later because it's cheap. Okay, but now the summary. You have a subgroup, free subgroup in another free group. If it's a finite index, it is distorted. Left-hand side inequality in the quasi-isometric phase. If it's an infinite index, not quasi-subjective. The second condition phase. So I would like to show you a quick proof of this lemma. If you have a subgroup of a finitely generated subgroup of a free group, which is of infinite index, you can find a quasi-morphism which vanishes on this group. So the idea is that you look at all words in your subgroup, and you want to find a word which is not a subword in any of these elements. So we call it a killer word. Yeah. And this will be the proof by example. Take a free group of rank 3 inside free group of rank 2. First generator is the commutator, second generator is the fourth power of the generator, and the third one is state. Draw this graph. So the vertex V0 is the base point. So you see the commutator here, A, B, A inverse, B inverse. You see before, B to the 4 here, and you see A to the power 3 here. So the fundamental group of this graph is free and two generators. And it's included in F2. So the inclusion in F2 goes like, take this graph, take your favorite figure eight, and go with every edge around the generator which is marked on the edge. Okay, so this edge from V0 to V1 will go to A inverse. The next one will go to A inverse, and so on and so on. So you have a simplicial map from this graph to the figure 8, which induces the inclusion of the free. In advanced terms, you can construct this graph from the corresponding covering by doing simple homotopy equivalence to this graph. And it has a name. It's called core graph in a paper of Stolz, so he does a lot of stuff with graphs and figures. Okay, how to construct a killer? This is our F3. So now observe that every path in this graph corresponds to a subword of an element of this group. Well, the loops at V0 are elements of the group, but paths, wherever they go, correspond to subword. So now I want to look at a word which cannot be obtained as a path on this graph. And the way we do it is observe that all the red vertices, they have edges either A or B inverse. For example, if you look at V4, it has the edge A, the edge B, and edge B inverse, but it misses the edge A inverse from your universal cover of the figure 8. So the idea is to construct
so B2 is not missing A inverse.
where
B2.
no, V2 has A and A inverse, it has B, but B inverse is missing.
So what's the property of red dots?
They don't have all generators of F2. Okay, now the algorithm. Start with the vertex x0, V0, go to V1. This gives you an element A inverse, and go to the void by degree. So this word cannot be obtained as a word starting at V0 because it has to go to V1 and then there is B. So now I check whether this word can be obtained as a subword from another. Well, if I start at V1, I have A1, B, so it is a subword starting in V1. but it finished in V3 where A is missing. So my new word is this. So this is not a subword obtained from a path starting at V0, and it's not a subword from the path starting at V1. But it is a subword obtained as a path starting in V2. So there is A inverse, B, A, and from B3, another A maps into the whole. And now I check whether this guy is a subword obtained from a path starting in every other vertex, and it's not. So my algorithm terminated, and this is the killer for this subgroup. Okay, so you can imagine that I presented a very special case of a general algorithm, and this is how you construct a killer word for you. Finally, generated subgroup of infinite index. Infinite index is important because you have red vertices. Otherwise, it would be a covering, and every vertex would have 4 edges in anything. So you couldn't do this. Thank you very much.
So for free groups, it makes sense not just to consider these conjugates of the basis elements, but to consider their orbits for the entire isomorphism group, which is much larger. So that would be like where you take all primitive elements.
Yeah.
So can you say anything about those Cayley graphs? Or about those
These metrics have also infinite diameter.
Yeah,
You can do a lot with quasi-morphisms.
right.
So for example, so maybe let me quote one nice theorem that on F2, there are quasi-morphisms which are invariant with respect to all automorphisms.
Right.
So, and this one, and there are many of them. So this is a theorem of Gradenburgsky Mashinkowski. So those quasi-morphisms will give you a lot of unbounded Lipschitz functions for your metric.
Yeah.
So this, and that's essentially all I know. So there are big metric spaces, whether they are quasi, and I didn't think I started with the simpler one. West.
What do you know about other computation invariant norms on free groups? I just looked at invariant and I wasn't for the series similar.
If you take an element, you can look at logs of its powers. If you get a sequence, you can divide by the exponent and compute the limits. That's sometimes enormous. But in your world, it's translation. Maybe. It's rational. So that's a recent theorem by Henry Assaf. Fun fact. Henry Assaf is last year when he proved the theorem, he was a schoolboy in Aberdeen. So it short.
It's not that short.
Oh yeah. Well, when he started talking to me, he was this, and then he's maybe that. He's now first year student in Cambridge. Then, so the fun fact is that, you know, I was playing with those figures a lot. He would come to my office. What are you doing? And I had the translation of the stuff on the board. Henry, prove that this is rational. 9 months later, he wrote a paper and now it's published. So, yeah, it's in the proceedings of the AMS. So, translational rational. He proved a bit more of that. And his proof is completely out of our world. It's very interesting. I know something about.
Are these things, if you these counting things, if you have to sort of modularize them, do they become take irrational values?
I just said no.
Oh, you said no.
Here, it's rational. So it's a. Yeah, so there's rationals, of course, Kaldauer's theorem about SCN.
Yeah.
Of a free group, this is rational. But the proofs are completely orthogonal. There is no geometry here. I know something about isometric embedding of the graphs in the Cayley graph. But you know, this Cayley graph is horrible. But for example, I can isometrically embed every cat zero, every one skeleton of every cat zero cube compass. So this gives you an idea that this space, it contains K to 3 subgraphs. So it's kind of on the one hand a bit weird. So it's not cat zero, but not far. I can embed one skeleton of a complex of injected words. So things like that. But okay, you would have to ask a very more specific question, and I can answer yes, no, I know, I don't, because it's in general, I would like more people to try to do this because I feel like there are only a few of us who think about this. This is part of advertising of a subject which is potentially interesting.
Yeah, sure. If there are no questions, that we can get.